example right here, and it's for an NPN transistor having this IS value and a B beta value, and it's connected as follows. So the emitter is going to be grounded, and the base is fed with a constant current source at a DC current of 10 microamps. The collector is connected to a 5-volt DC supply via a resistor, RC, of 3 kiloohms, which we have right here. We assume that the transistor is opening in the active mode. So we need to find our VBE and VCE. We need to use these values to verify active mode operation, and then when we're done with that, we're going to replace the current source with a resistor connected from the base to the 5-volt supply. So we are going to replace the 10 microamps here, and we're asked what resistance value is needed to result in the same operating condition. So we're going to do that next. First, we're going to look at the notes on the right. So we have our forward active region, and the reason why it's forward active is because we're about to find out that our B is much less than our C. So the base voltage will be smaller and the base collector than the base collector. So base current is going to be smaller than base collector, which means it's reverse bias. The base current is to the left right here, the base, and then our current, the collector, the base collector is to our right. So we have our base to the left and then our collector to the right. And since that is true, that means that we are going to be reversed, because typically our base goes like this way from left to right, but we would be going from right to left if the collector is bigger. So that's just something to note. Now we're going to solve for this problem. We have the solution below and we're going to walk through it. So with our circuit right here, it shows the circuit as described with the transistor represented by the model, and this is just for our notes. So we're going to determine our VBE with the exponential characteristics of our dB as follows. If we look at the notes linked below the like button, page 103, we are going to have these two equations. And we are going to rewrite the first one so that it looks like what we have in our solution. So if we want our E to not be an E, we're going to have to multiply everything by ln. So we're essentially going to have an ln, and then if we divide both sides by our is first, we're going to have an IC, and then an is in the denominator. This is equal to a VBE, and then we can of course multiply both sides by VT to get VBE by itself. Now, we weren't given a I of C, so we're going to want to replace this. We can rewrite this down here as I of C is equal to IB, and then we are going to have this being multiplied by our B, and so we can rewrite this as VBE is equal to our VT, and then we have our ln with our IC, which is not really going to be our IC anymore. It's going to be our IB times the beta, or they write it like our IS over B. And that works too, right? Because if we were to multiply both the numerator and denominator, we multiply the beta in both of them. So now we're just going to plug in our values. Our VT, we've looked at this previously, it's just K times T over Q, and this is usually written as like 26, I think it's in millivolts, so it's 26 here, but the author of the book, he mixes up 26 and 25, and typically it's 25, but sometimes he'll use 26, so that's just important to note. Here he uses 25, and this is 25 millivolts again. So then we have our ln. In our ln, we are going to have our IB, which we're given up here as 10 to the, or that's not IB, so IS is 10 to the negative 15. That's going to go on bottom. Our IB is going to be the 10 times 10 to the negative 6 for our microamps, and that's going to go up top. So we're going to have all of this here, and that means our VBE is going to equal to 0.69 once we plug in our values. Now we're going to find our VCE. And VCE is just going to be the voltage right here minus the voltage across the region that we have in red right here. And that's going to give us the VCE down here. So our VCE is going to be equal to the 5 volts minus our RC, of course, right here, times our IC. So we're going to have the 3 kiloohms for the resistance times our, again, IC, but where we given our IC doesn't look like it. And in fact, we substituted it in here. So we can find our IC by using this equation, or since we know our IB and we know our beta, we could just plug in those values. And that is going to give us the answer for this. So if we plug that in, we are going to get our 100 for our beta, and then 10 times 10 to the negative 6 for our IB. That's going to give us 1 milliamp. And so we are basically just going to have 5 volts minus our RC, which is 3 times the 1 milliamp. That's going to give us 2 volts. So that's the answer for that part. Next, it's asking us if we replace our 10 milliamps with a resistor right here, and the resistor is a value that we need to find. It's going to be the same, the resistance value is needed to result in the same operating conditions. So everything else but the resistor is the same. So since this is reiterating what we said earlier, Vc is at 2 volts, which is higher than our Vb, which is at 0.69 volts. So B is less than our C. The transistor is indeed operating in the active mode. This is forward active. Now we're going to replace the 10 microamp current source with a resistor RB connected from the base, the 5 volt VDC current VCC as in figure 6.6b, and the value of RS, or RB, or that is RS. Oh, it must be what? And that's actually RB. So the font's kind of small, but RB right here, we're going to find it as the voltage between here and the voltage between here. So we are going to have 5 volts minus our VBE over the resistance, and that's what we're given here. So our RB is equal to the 5 volts minus VBE, which we found to be 0.69 volts, and this is happening over our resistor, which is the 10 microamp, or not the resistor, sorry, the current, because we're using the equivalent of Ohm's law here. So we have voltage over current, and that's going to give us our resistor value. So the previous current is 10 microamps. We're just finding the resistance of this part, and that's going to be 431 kilo ohms. And that's how we would look at this problem using the notes linked below the like button in the description.